All right, let's get started. So this is the last class of this semester, chapter 9. We are going to discuss physical design for database system. All right, in the previous chapter, we discussed the logical design process for database system. Well, let's do a quick review. In chapter 8, we learned two processes for logical design. First, we used the ER and ER diagram, that is entity relationship and extended ER diagram, to describe the logical data design. And also, we learned another tool, that is DFD diagram, data flow diagram, to describe the physical process design. So today, we are going to focus on the physical design. We will first see how the logical data and process models are converted to physical models. Well, what is physical model? Actually, you can simply think that physical model or physical design is tables. Different tables in the database system. If you can recall our database in Access, you will see different tables, right? So these are the physical design of the database system. How to convert the logical design to physical design. That is what we are going to discuss in this chapter. Whereas the logical design is independent of any particular implementation of the model. Physical design is tied to a particular implementation path. Well, as we alluded to earlier, the implementation mechanism we will focus on is relational database system. In this chapter, we will show how the DFDs map to forms in a relational DBMS, database management system, with form inputs and outputs mapping to tables in the database. The process of ensuring that tables in a relational database do not have any undesirable flaws. This process is referred to as database normalization. And well, database normalization will also be discussed in this chapter. Okay, first of all, let's look at the conversion rules. Well, in the previous chapter, you have learned about the ER diagram, that is the logical data design of the database system. Now, you have the ER diagrams to the tables, but the problem here is how to convert ER diagrams into tables. Well, we first indicate the rules and then illustrate the application of rules with an example. before we get started, please note that we have two rules to think about. When you look at the ER diagram and convert it into the tables, well, the first thing you need to look at is the optionality of relationships. And the second thing you need to look at is the cardinality of relationships. Okay. First of all, let's consider the case of mandatory relationships. If you can remember, mandatory relationship is represented with a bar adjacent to that object in the ER diagram. Okay. There are several rules for the cardinality of relationships: one-to-one, one-to-many, and many-to-many. So, first of all, let's look at the rules of converting one-to-one relationships to tables. Okay. For one-to-one relationships, we first collapse the entities participating in the relationship into a single table. Second, for relationships other than one-to-one relationships, we need to create a separate table for each other. Then we create fields for each table based on the attributes identified in the ER diagram. Well, here, if you can recall the advantage of ER diagram over basic ER diagram, you will see three more things. That is, the first two is ER diagram show the optionality and the cardinality of relationships. And lastly, the ER diagram shows the fields or the attributes of each different diagram. Well, let's continue. And then we designate the primary key in each table based on the attributes. Well, this is one-to-one relationships. And we said for any relationships other than one-to-one, we create a separate table. So let's take a look at one-to-many relationships. The rule is to post the primary key of the table on the one side of the cardinality to the table on the many sides of the cardinality. The posted key becomes a foreign key in the table on the many sides of the cardinality. And for many-to-many relationships, we create a new table for the relationship and assign the primary key for each participating entities to a new table, resulting in a composite key for the new table. If you can recall the composite key, yes, the composite key is used right here. So a quick review. What is composite key? Composite key, well, it is similar to the primary key. The only difference is the composite key uses more than one field. working together, more than one fields working together to identify one specific record in a table. And then we add any attributes unique to the many-to-many relationship as non-key attributes in the new table. If there are no attributes unique to many-to-many relationship, notes that the composite key table will be a all-key relation. So that means a table with no non-key attributes. Well, the above rules are applied to convert the system design implicit in the ER diagram into relational tables. But it may occasionally be necessary to create an additional table to store reference data that was not explicitly identified in the diagram. For example, most organizations would find it convenient to have a table that stores the zip code for all the states, even though the zip codes were not explicitly indicated in the ER diagram. And another example is a table containing tax rates would be convenient for a payroll system. So now let's consider the following ER diagram of a mandatory relationship between two entities. Two entities are cellular phone and salespersons. Okay, now you should be able to interpret the above ER diagram based on our discussion in chapter 8. Recall the notion used in the ER diagram. The bar against the entity symbol, that is this part. A bar against the entity symbol indicates that the entity's participation in this relationship is mandatory. And in this diagram, the bar against both entities indicates that every salesperson must be assigned exactly one cell phone, and every cell phone must be assigned to exactly one salesperson. Well, since it is a mandatory one-to-one relationship, we apply the first conversion rule and collapse all the entities into one table, as shown in this slide. So this is the resulting table. Well, again, this is a mandatory one-to-one relationship. So let's go back to our rules and take a look. Our rule for one-to-one relationship is simply to collapse the entities participating in the relationship into a single table. So in this diagram, we have two entities, cell phone and salespersons, we know that the relationship is mandatory one-to-one. So again, that means every salesperson must be assigned exactly to one cell phone, and one cell phone must be assigned to exactly one salesperson. So, two entities. We collapse two entities into one table. Salesperson, the primary key is SPNO, salesperson number, with all the attributes assigned to this table, including name, address, date, employee, department. Well, next, let's take a look at the other object, that is cell phone. Cell phone has four attributes. They are phone number, carrier, monthly charge, and payment date. Okay, so regarding the designation of primary key, you can designate either SPNO or phone number to be the primary key, since they both uniquely identify one row in the table. Well, let's take a look at the second example, that is mandatory one-to-many relationship between these two objects. Okay, as you may recall from the discussion from the previous chapter, a cross-foot, this part, a cross-foot against salesperson's entity indicates a many cardinality. Well, the scenario depicted in this diagram indicates one cell phone is shared by many salespersons. You should note the bar against both entity symbols continues to indicate the mandatory nature of the participation. So that means one cell phone is shared by many salespersons by adding this cross-foot, and at least one salesperson, indicating by this bar against salesperson. Well, the environment in which the scenario makes sense is in a large department store where each area is assigned to one cell phone, and there would be obviously many salespersons in the area. Perhaps the department store uses the cell phones to allow its salesperson to be flexible to move around the area. Well, the application of rules can be applied to this scenario. So let's take a look. So it says for relationships other than one to many, we create a separate table. And for one to many relationships, we post the primary key of the table on the one side of cardinality to the table, to many sides of cardinality. Okay, let's take a look. So we create two tables, each for cell phone and salespersons. And we post this. I mean, the primary key of cell phone as the foreign key to salesperson's table. So you will see the posted key becomes the foreign key in the table on many sides. Cardinality. So this is the posted key becomes the foreign key of salesperson, where the cardinality is many. Okay, let's look at the second case. Mandatory many to many. Well, the cross votes against both entity symbols in this diagram indicates that a salesperson is assigned to many cell phones. So it may mean that, for example, perhaps salespersons are allowed to work in many departments and they work with different cell phones in each department. So, as before, cell phones are assigned to multiple salespersons in a department. Mandatory many to many relationships are dealt with applying the last rules. That is, a new composite key is created using the primary keys from each table participating in the many to many relationships. So let's look at the last rule. To create a new table for relationships and assign the primary key of each participating entities to the new table, resulting in a composite key for the new table. So in this case, this is the new table with composite keys, and each key is from each different object And in this case, as you can see, SP number is right from the primary key of salesperson's table, and phone number is derived from cell phone table. So this is the conversion rules for mandatory relationships. And next, well, let's take a look at the rules for optional tables. Well, the rules are pretty much simple. First, to consider all the optional relationships as having many cardinality, whether or not the relationship is actually a many relationship. And second, to ignore the fact that relationships are optional and apply the above 6 rules for mandatory relationships. Okay, let's take a look. So in this diagram, it is optional one-to-one ER between these two objects, cell phone and salesperson. Okay, let's see. We first consider all optional relationships as having a many cardinality. So we can see in this part, we have a circle indicating optional participation. We can regard it as having a many relationship. So in this diagram, it is now mandatory one-to-many. So now we can convert this fictitious mandatory one-to-many relationships to tables. Well, we follow this rule, the 5th rule, mandatory one-to-many. We follow this rule, and let's take a look. Okay, we create one table for each object. That is one table for salesperson and another table for cell phones. And post the primary key of the one side as the foreign key to the object with many sides. So we post salesperson's number as the foreign key on the other side or on the other table. Okay, one more thing. How did we prevent null value? We have 3 things to consider. The alternative of collapsing both tables into one. Another option would be to create 2 separate tables and post the key of cell phone table to salesperson table. each alternative would result in many null values and not desirable. So next, let's see optional one-to-many relationship between two objects. And same thing, you can regard this part, optional participation, as many. And just follow the rules. That is many-to-many relationships. Mandatory many-to-many. And similarly, for optional many-to-many, we can disregard these two parts as many. Oh, there has been a many crown's foot here on salesperson side, and there has been a crown's foot on cellular phone's table. So we convert this ER diagram following the rules of mandatory many-to-many. Well, this is a summary of conversion rules. Well, conversion rules is the first thing that you need to know about in this chapter. This is the second thing you need to know in this chapter, database normalization. So far in this chapter, we have discussed the process of converting a logical data model to a physical model suited for implementation of a particular DBMS. In particular, the conversion rules are aimed at converting a ER diagram into tables for implementation in a relational DBMS. The database system in most organizations nowadays are relational database management system, such as Oracle, Microsoft SQL Server, or Informix, or Ingress, etc., etc. Many database DBMS systems. Small business would probably find Microsoft Access to be sufficiently powerful for their needs. It is possible that in the future DBMS will be something other than the currently popular relational database. Perhaps object-oriented DBMS may be a preferred implementation platform. But for present, the vast majority of logical models are implemented in a relational database management system. So the need to convert the ER diagram into tables is necessary. Prior to implementations in a relational DBMS, it is necessary to ensure that the database design is not flawed. So the process of database normalization seeks to ensure that there are no significant data anomalies in the database design. So in essence, we are seeking to ensure that the tables in a relational database conform to good relational database design in principle. Application of the rules described previously to convert ER diagram to tables automatically result in well-designed tables. In most cases, the resulting tables are already in third normal form, which will be explained later. But a few design flaws may still remain in the tables that result from mechanical application of the conversion rules. It is also possible that you may encounter a relational database system that was developed without employing ER modeling. So system and analyze and designers may simply have determined the fields to be represented in the database and have organized the fields into database using some ad hoc method. It is clearly possible that tables in a relational database that you encounter could have serious design flaw, as will be explained below. So, simply speaking, a normal form simply means a table conforms to certain rules aimed at testing the integrity of the table structure. Okay. So regarding the design flaws, let's see, what can a design flaw result? What are the results? There are data anomalies. There are three kinds of data anomalies. There are insert anomaly, delete anomaly, and update anomaly. An insert anomaly is the inability to insert or add data to a table because of the design problem. Delete anomaly literally means that deleting certain data from a table results in the loss of other related data. And the loss of other related data is write the data that the user would like to retain. And finally, an update anomaly means a change in a data item must be performed in multiple locations rather than just one. Well, the system designers and users who obviously like to minimize the number of data anomalies in the relational database. Increasing levels of normal forms indicates that the table conforms to stricter rules, with consequently fewer data anomalies. So before we get to know three levels of normal forms, we need to know about functional dependency. So to describe the process of database normalization, we need to consider the concept of functional dependency. In a table with fields x and y, if there's only one possible value of y for every value of x, then in this case, y is said to be functionally dependent on x. In simple terms, field x determines the value in field y. You're already aware of the concept of primary key and non-key attributes. Well, the functional dependency notion simply means that all the non-key attributes in the table are functionally dependent on the primary key. But as you will see later, it is possible for a table to have a functional dependency that doesn't originate from the primary key. So let's consider an example to explain functional dependency. In a table containing the data about a student, not only one student, but many students. For every instance of the student's ID number. For example, in Rutgers University, we have RUID. Well, for every instance of RUID, there would be exactly one name. Of the particular students. So, in other words, a particular student will have only one name. So, in this case, name is functionally dependent on RUID. But since it is possible that two or more students could have the same name, this relationship doesn't work in the other direction. So in other words, we cannot say that RUID fields is functionally dependent on name. So that's why functional dependency work in only one direction. Okay, let's turn to an example to illustrate this point. A department in a business school would like to store information in a database about professors, their offices, and courses taught by professor. In addition, the department wants to keep track of professors' teaching preference in terms of days and time. So the fourth object is teaching preference. Obviously, the same course can be taught by different professors, and a professor can be teaching multiple courses. So we can include all 9 attributes into one table. Professor number, name of the professor, office number, and this office is phone number. Course number, course description, and credit hour. And the last 2 attributes are the preference of each professor's teaching schedule. Okay, let's see. Well, first of all, let's talk about first normal form. Okay, this is an example of non-normalized relation because it contains a repeating group. Simply stated, a repeating group results when there are multiple values. That's the intersection of certain rows and certain columns. So, for example, in this table, we can see repeating groups here. And also here, and here. Also, we can find repeating groups here. Oh, and additionally here, as well as this row. They are all repeating groups. Okay, the only row that does not contain repeating group is the second row. So this is an example of non-normalized relation, simply because of repeating groups. The existence of multiple values, self values in one or more non-key attributes for a single primary key value is called repeating groups. So a relationship is said to be in first normal form must have exactly one value in each cell. Or in other words, that is, the first normal form relation has no repeating groups. So what can we do? We redesign the cells and separate it into two tables. So the tables showing in this slide shows how the repeating groups in the previous table is eliminated to create tables in first normal form. Essentially, the previous table is decomposed into two tables. Professor table, which contains information about professor name, professor number, professor's name, office number, and phone number for each professor. And another table, course preference table, which contains data about professor preference for courses. Each of these two tables is in first normal form because they do not contain any repeating groups. As will be discussed later, professor table is also in second normal form. Well, the primary K in each table is underlined. But please remember, in the first normal form table, all the non-K attributes should depend on the primary K. So let's take a look at the data anomalies in first normal form. First, let's look at insert anomalies. Well, in the course preference table, information about a new course cannot be added until a professor indicates a day and time preference. It is not possible to add a new course information. So this is insert anomaly. Unless a professor indicates the preference for this course, it cannot be added because the primary K in the above table is composite K of professor number and course number. Adding a course with a course number while leaving the professor number blank would be a violation of entity integrity. So entity integrity was discussed in chapter 6. Under the requirements of entity integrity, the primary K cannot be null. So this inability to add data to the database is called an insert anomaly. That is, the user is not able to insert data because of the structure of the table. And this anomaly will be discussed later. Let's see how to avoid it by redesigning the course preference relation. So this is insert anomaly. And next, let's discuss update and delete anomaly. Well, if the description of a particular course is to be modified, the change will have to be performed multiple times rather than just once. As you can see in this table, the course description for the same course is repeated multiple times. For example, the course information about AIS class appears once here, twice here. Well, if you want to update its information, for example, you want to update the credit hours for this course. You change from 3 to 4, for example. You need to change it here, 1 for the first time, and change it here for the second time. So this is update anomaly, which means update of data is performed more than once. Ideally, the user should have to update the course description just once for a particular course. This duplication of the update effort is called an update anomaly, and it is also avoidable by redesigning the table. So finally, let's consider the problems associated with deleting data. Let's see how deleting anomaly happens here. Let's assume that a particular course is taught by only one professor. If that professor leaves the university and his record is deleted from the database. But in this case, we also lose the information about that course taught by this leaving professor. So this is inadvertently the loss of data is called delete anomaly. And also, delete anomaly can also be avoided. To understand why these anomalies occur, let's consider the structure of this course preference table in detail. The primary key in this table comprises the professor number and course number. That is a composite key actually. But the only fields that dependent on both professor number and course number are the day preference and time preference. These two attributes are the only attributes which have functional dependency of the composite K. Well, these two attributes indicate the preference of a professor for a particular course. But for description and credit hour attributes, all you need to know is only course number. So, formally speaking, these two attributes are functionally dependent on only one K attributes, course number. So this is the causes of these data anomalies. The course preference relation is in first normal form, but as you know, it is not in the second normal form. We just found the reason because there are partial dependency on the primary K. So in other words, not all the non-K attributes in this table are fully functionally dependent on the entire primary K in this table. Well, the solution is to decompose the first normal form course preference table such that independence information is independently represented. So to convert a table from first normal form to second normal form, dependencies are dependent on only a part of the primary K that are split up into separate relations. So we have the rule for second normal form. That is, first of all, it is in first normal form, no repeating groups. And second, the non-K attributes in the relation are functionally dependent on the entire primary K. Or in other words, there's no partial dependency. No partial dependency. Well, if you look at the professor number, professor table in the previous slides, yes, the first table, professor table in this slide, it is already in second normal form because because every non-K attributes depends on the entire primary K. where in this table, there's only one primary key, that is professor number. So we can say that this table is in the second normal form. Well, let's see how to resolve the problems in the second table. To redesign it, or simply speaking, to decompose this table into two tables. Well, two tables, courses table and course preference table. Well, as you can see in this slide, the course description and credit hour fields now have an independent existence since they have represented in the courses table. Both the non-key attributes in the course table are functionally dependent on the primary key, course number. The preference table has two non-key attributes, date preference and time preference. And both of them are functionally dependent on the composite key, professor number and the course number taken together. So both the course table and preference table are in second normal form. As we will discuss, they are also in a third normal form. Note that application of the conversion rules stated earlier will automatically result in tables that are in second normal form. But you may encounter an existing database design in which you may be called upon to ensure that the tables are in second and third normal form. So let's take a look at of the data anomalies in second normal form table. Let's go back to professor table. It is only in second normal form. Well, now let's assume that there is exactly one phone in every office. So there can be only one phone number associated with a given office. In a sense, what we are saying is that the phone number non-key attribute is functionally dependent on office number, which is also a non-key attribute. This dependency between two non-key attributes in the table is called transitive dependency. Okay, let me show it. Phone number is functionally dependent on office number, but office number, both office number and phone number are non-key attributes. Well, Put another way, any functional dependency that doesn't originate from the primary key in a table is considered a transitive dependency, which is what can potentially cause insert, update, and delete anomaly in a second normal form. But if the phone number field refers to the professor's cell phone, what would not change is the professor was moved to a different office. Then there's no connection between the office number and the phone number. In that case, there's no transitive dependency in the professor table, and that table would be in third normal form. So it is essential to carefully examine the assumptions that govern the dependencies between attributes in the table. Well, returning to the assumption that an office can have only one phone. The problems in this table stem from the fact that information about offices and phone numbers does not have an independent existence. Rather, this information is tied to information about professor. So let's consider the kinds of problem that the lack of independent existence for office and phone information poses. It is not possible to add information about a new office and phone number until a professor is assigned to that office. So in a business school, it is possible that we have some empty offices reserved for future professors. But in this case, it is not possible to add an office information until a professor is assigned to that office. Also, when the professor record is deleted, we also lose the office and phone number information that we want to retain. Well, the solution is also to further decompose the second normal form relation such that all data that is independent of other data are stored separately. So the solution is right here. We decompose professor information and office information into two tables. So this is a table in third normal form. We can say that a relation is in third normal form if first it is in second normal form. Second, all functional dependencies in the relation originate from the primary key. And the third requirement is the relation contains no derived fields or no transitive dependency. So this is a summary of 3 normal forms. In summary, we can say that if a table is in first normal form if there's no repeating groups. In second normal form, we can say a table has no partial dependency. And the table is in third normal form, which are tables contains no derived fields or tables without any transitive dependency. So please note that it may be acceptable sometimes to violate third normal form in certain instances, so long as you realize what is lost by non-conformancy to third normal form. Well, in the above example, the professor second normal form table with the fields professor number, name, office number, and phone number may be left in second normal form if it is not considered critical to keep track of offices and the phone number. Thus, the insert and delete anomalies outlined for second normal form professor table may be deemed acceptable, and the organization may decline to leave the professor tables. Maybe may decide to leave this table just in second normal form. It is important to realize that the normalization are just some guidelines, and the common sense should prevail in database design as you consider the consequences of violating any of the normal forms. You should think in terms of the anomalies that result from the violation. That is, what are the insert, updates, and delete anomalies that result from violation of normal forms? If these anomalies are undesirable, then the normalization violations should be corrected. The process of database normalization can be mastered only by practicing these normalization techniques on sample or some real world problem. So this is the end of this chapter. And also, this is the end of this course. So thank you very much, everybody, for your attendance to my class.